All right, so we are on to examples from chapter 8. So let's do 8.12. So in 8.12, dry compressed air at a TMI, so the inlet mean temperature, is 75 degrees Celsius. The pressure is 10 atmosphere. The mass flow rate of 0.001 kilograms per second enters a 30 millimeter diameter, 5 meter long tube whose surface is at TS equal to 25 degrees Celsius. For part A, they determine the thermal entry length, the mean temperature of the air at the tube outlet, the rate of heat transfer from the air to the tube wall, and the power required to flow the air through the tube. For these conditions, the fully developed heat transfer coefficient is H equals 3.58 watts per meter squared Kelvin. Okay, so they told us we have dry compressed air. The inlet mean temperature is 75 degrees Celsius. The pressure is 10 atmospheres. The mass flow rate is 0.001 kilograms per second. The diameter is 30 millimeters, which is 0.03 meters. The length is 5 meters. Surface temperature is 25 degrees Celsius, and the H convection coefficient for fully developed flow is 3.58 for fully developed. They want us to find the thermal entry length. Let's make that a little nicer. Thermal entry length. The mean temperature of the air at the tube outlet. So the mean air temperature at outlet. They have the rate of heat transfer from the air to the tube wall. And then lastly, the power required to flow the air through the tube. All right, so our schematic, this is all for part A here. We have our tube. we have our air flowing in. With a mean inlet temperature. Easier to read. Flows out at some mean outlet temperature. We have surface temperature, and then we have some geometry here. So it has, tube has some length to it. Diameter. So assumptions. Steady state. And we have some analysis, right? All right. So where do we want to begin here?
I would start with finding the Reynolds number.
The Reynolds number, okay. So within internal flow, we have a nice version of the Reynolds number that deals with mass flow rate. Okay, so this is for a circular tube. Okay, they just put in mass flow rate, density, velocity, and area, and so for basically velocity, when they substitute it in to the original Reynolds number, we can manipulate it and you get this nice one we see here. Okay. All right, so let's look at this equation. We have mass flow rate given to us, right? Diameter given to us. We need to figure out our dynamic viscosity, okay? So at what temperature do we take this at to go get that dynamic viscosity? All right, we need to take it at the mean temperature, right? So the mean temperature is the inlet, the average of the inlet and the outlet. Okay. And that's for, let's change the color here. Heat transfer properties. Okay, and then there's a friction, or film temperature, which is the mean average plus the surface temperature divided by 2. And that's for hydrodynamic properties. So the fluids kind of side those properties. Well, we don't have the outlet temperature, right? That's part of what we're going to have to solve. So that means we're going to have to assume something. Okay. And a good place to start would be looking at what's going on here, right? We have 25 degrees Celsius entering, and the walls are at surfaces at, entering at 75, and the surface is at 25. So that means the outlet can only get up to a temperature, I should say, a temperature of 25 degrees Celsius. So we're gonna have somewhere in between there, okay, from the inlet to the outlet. So a good place to start would be looking at those two temperatures, the inlet and the surface temperature. Okay. So I'm going to take kind of like a temperature of 320 Kelvin. It's kind of really close to the average of the inlet temperature and the surface temperature. I'm also just going to say that the film temperature is the same. All right, so all that, we can get our dynamic viscosity. We have 1.94 times 10 to the negative fifth seconds per meter squared. All right, so now we go back up here. We have our dynamic viscosity. Reynolds number is 2187. So what does that tell us? Laminar, okay. So we're less than 2300, right? So we're laminar. Okay. All right, so we know whether we're laminar or turbulent. So now what? All right, so they're first asking for the entry length, right? Thermal entry length. So let's just start there, right? We know laminar entry length, okay? So fully developed for the hydrodynamic, it's going to look like this. For fully developed for the thermal, it's going to look like this, okay? So diameter was given. We have our Reynolds number. We need to get our Prandtl number. So this is table A4, same place. So now we have Prandtl number. So we then can solve. So hydrodynamic distance is 3.28 meters. Thermal is 2.31 meters. And if we go up, our length is 5 meters, right? Oops. So what does that tell us?
It'll reach a fully developed flow.
Yeah, so we're fully developed, okay? So we're also fully developed hydrodynamically. And thermally, right? So if we were, we saw ours, our Prandtl number is 0.7, so it made our thermal distance just smaller than the hydrodynamic distance, right? A little bit smaller. But if we had a high Prandtl number, our thermal could be much higher than our hydrodynamic. Okay, so then we could be fully developed hydrodynamically, but not fully developed thermally. Okay, and that has implications then. All right, so we solved this one, which was part of our, what was being asked right here. Okay. Now we need, in this list of things to solve for, it asks for the mean air temperature at the outlet. Okay. So where would we begin for that? What situation do we have here? Okay. When we were in chapter 8, we had these different situations in the early section, and then that carried over to the later section of slides. We had these constant heat flux boundary condition. We had constant surface temperature boundary condition. Then we had constant external fluid temperature. Okay, so which one do we have in this situation? What is this right here telling us?
We have constant surface temperature.
Yeah, so we have constant surface temperature. It gave us 25, the surface is 25. So it doesn't matter what else is happening out here, okay? The surface temperature is always staying 25. And since that's staying 25 all along here, and the temperature of the fluid's changing as it goes through, right? That means the heat flux would change as you go through. So it can't be constant heat flux as the other side of it, right? And then this being held constant, doesn't matter what's happening in the external fluid side. So this would be a situation, they're just telling us the surface temperature is constant, but this would be a situation where there's a fluid on the outside that's condensing or boiling, right? If you had boiling water on the outside of the tube, it would hold the temperature to our 100 degrees Celsius, because that's the temperature of boiling water. So that would hold that constant temperature, that boundary, right? Same with, condensing. So same idea there, okay? So that's where a constant surface temperature boundary condition really comes from, but we just usually have a temperature given to us. All right, so we have then constant surface temperature. Okay, so this is where, now those three different conditions, we were able to develop equations in our slides for that, right? For the outlet. Oh, let me write this in black. All right. So we developed this in the slides, the equation, and we even used it in some of those quicker examples in the PowerPoint. Okay, so if we look at this, we have diameter, length. So this is also the same as perimeter, right? Is pi d. So that's what we have. Or I shouldn't say this d times L. Let me rewrite that. All right. So that's perimeter. Okay. We have length. We have the perimeter because we have diameter. Mass flow rate was given in the problem. Surface temperature, inlet, air temperature. The CP we need to find, right, from our table. So table A4, we get our CP value. And that is 1008 joules per kilogram Kelvin. Okay. Last is our convection coefficient. Okay, they told us in the problem, they gave us a convection coefficient right here for fully developed flow. Okay. So can we use that one?
Yes.
Yeah. So we determined we're fully developed. So it happens to be, we can use that one, right? But if, you know, they wanted to be really tricky, they could have gave you the H for fully developed, but it wasn't fully developed. So then you would have had to go and grab something differently. Okay. So those, whether it's fully developed or not fully developed, really changes the convection coefficient and the equations you have to go get to determine that convection coefficient. So in this case, it is fully developed. And so then we can use the H that we were provided in this problem, okay? And so we have everything there, okay? So then the outlet temperature ends up being 34.4 degrees Celsius, which is 307 Kelvin. Okay. All right, so that was this one. All right, so now we need the rate of heat transfer, all right? This is from rate of heat transfer from the air to the tube wall. So where, or how do we get that? So if we're looking at our schematic here, right? So that's the rate of heat transfer from the air to the tube, right? So if we're do this, and this is our tube, and this is the heat transfer. What would we be able to do to solve that?
Would it be the mass flow rate times specific heat, and the difference of the inlet, the outlet, and the inlet temperatures?
Yep, and that is really just COE, right? If we're looking at this fluid boundary, we're carrying in enthalpy in, carrying out enthalpy with the mass flow rates carrying in enthalpy, mass flow rates carrying out, and then we're simplifying enthalpy as Cp times T times temperature, steady state, neglecting kinetic and potential energy. So our equation simplifies for our COE. There's no work. Oh, all right. So our COE just simplifies the mass flow rate, Cp, and the change in our temperatures, right? So that's just conservation energy being simplified there. Right? If we look at that, we have temperature in, we solve for temperature out, we have mass flow rate, we already grabbed Cp. So then we get Q is equal to negative 40.9 watts. Oh, he's blue. Okay, so we go back up, we have Q. All right, so then last is power required to flow the air, okay? So if we're pushing this air through this tube, right, and it's asking us for the power required to do that, what are we kind of overcoming to do that?
Pressure change?
Yeah, so our pressure change, right? So power is change in pressure times volumetric flow rate, right? So we're gonna end up needing equations for both. Those weren't given, right? So pressure change just comes from our friction, right? We just have a horizontal tube. There's no height change, nothing. So we're just have our drop in pressure related to our friction factor. Okay. So let's go through that and see. So now we have something for delta P, a relationship. We don't have a friction factor. We don't have density yet. The mean velocity. We do have length. We do have diameter. Okay, so we got to go through and figure these out, right? So we'll start with the easiest one, density. So we can get density in tables A-4 or ideal gas law. With pressure over RT. And we get, if I can find it, 10.95 kilograms per meters cubed. All right, so now we got that. All right, so then how do we get volumetric flow rate? So this one. What do we know that could possibly get us there?
Mass flow rate.
Yeah, so we have mass flow rate, right? density times volumetric flow rate, right? So we have volumetric flow rate is mass flow rate divided by density. So we have density, we have mass flow rate. So now we have volumetric flow rate, okay? All right, so then mean velocity. How do we get that? Any ideas?
From the Reynolds number. And like going back to the other equation.
Yeah, I mean, you could do that. That's a kind of the long way. So there's an equation that the reason, let's go back up there then. Gosh. So there's the equation really that it comes from is this one. Okay, but yeah, you would get there because you're rearranging that equation, basically what you're ending up solving for. Okay, so that would work. Okay, but the more kind of direct, let's say, is that mass flow rate is also right density velocity times area. That's the equation we use in thermo, but that velocity that we've always been using in thermo is the mean velocity. Okay. So then rearranging that, which is just a cross-sectional area. All right, so we look at that. We have mass flow rate, diameter, density now. So that gets us mean velocity. Okay. So then last is our friction coefficient. So where do we get that from?
Okay, I just
64 over the Reynolds number.
It's something that you.
Yeah, it was there. Okay. So we get to use the 64 over the Reynolds number because it is laminar, right? So that's where we get to, make the easier case here. Otherwise, yes, we got to go to that Moody diagram and figure out what our friction factor is from it. Or if we had a smooth pipe and turbulent flow, there is an equation for the friction factor. But if not, we have to go to those surface roughness and those equations you dealt with in fluids, right? So in our case, we have friction coefficient and it being laminar. Okay, so that makes it seem like friction coefficient is easy to solve, right? But as you saw in fluids, it's can be a little bit longer to solve. All right, so 64, we have a Reynolds number given. Actually, I don't think I have the friction coefficient directly solved, but we have enough then. So we have friction coefficient. So now we have everything to solve for our power. Okay, we have our equation for delta P. We have everything there. We've checked everything off, so we can go through and get all our in-between values or substitute it all back into that power equation and have one big equation. But if either way we do that, we're going to get a power of 446 watts to drive this flow. Okay. Any questions on that? All right, so let's do another problem. Let's do 8.26. 8.26. Air at pressure is 1 atmosphere enters a thin-walled, so diameter of 10 millimeter long tube with a length of 2 meters at an inlet temperature of TMI equals 100 degrees Celsius. A constant heat flux is applied to the air from the tube surface. The air mass flow rate is 270 times 10 to the negative 6 kilograms per second. And part A is if the tube surface temperature at the exit, TSO, is equal to 160 degrees Celsius, determine the heat rate entering the tube, evaluate properties at temperature equal to 400 Kelvin. Part B is if the tube length of part A were reduced to a length of 0.2 meters, how would flow conditions at the tube exit be affected? Would the value of the heat transfer coefficient at the tube exit be greater than, equal to, or smaller than the heat transfer coefficient for part A? And then part C is if the flow rate of part A were increased by a factor of 10, would there be a difference in flow conditions at the tube exit? Would the value of the heat transfer coefficient at the tube exit be greater than, equal to, or smaller than the heat transfer coefficient for part A? All right, so we have air. Has a pressure of 1 atmosphere. It's thin-walled. Thin-walled long tube. So our diameter is 10 millimeters, 0.01 meters. Our length is 2 meters. The mean inlet temperature is 100 degrees Celsius. It's a constant heat flux. The mass flow rate of air was given, 270 times 10 to the negative 6 kilograms per second. They want us to find for part A, the heat rate entering the tube. Heat rate entering tube. So that's Q, but they also give us that in part A, the tube surface temperature at the exit. So the exit tube surface temperature TSO is 160 degrees Celsius. And they say to evaluate properties at a temperature of 400 Kelvin. So that's saying the average mean temperature is 400 Kelvin for properties. And that mean temperature is equal to that kind of film temperature. Part B is the length is now 0.2 meters. And they're looking for what would the flow conditions at the tube exit, how would the flow conditions at the tube exit be affected? So of exit flow conditions affected, question mark. And then we'll have, they also ask for the convection coefficient at the exit. So up, does it go up, down, or stay the same? Part C is now mass rate 10 times the original mass rate. So are the exit flow conditions affected? And then also again H at the exit. Does it go up, down, or stay the same? Okay, let's draw our schematic here. All right, so we have length, diameter, the mean inlet temperature, and they also give us this the outlet surface temperature, and then that's the mean outlet temperature. And then they said constant heat flux, right? Okay, so if we're looking at this, we're looking for part A, this heat rate entering the tube. Where do we begin?
COE.
COE, okay. All right, COE around that tube. we get Q mass flow rate CP mean outlet temperature, inlet temperature minus inlet. All right. So let's take a look. We have mass flow rate. We need to get CP. We have our inlet. We would need to get temperature at the outlet, and also we're unknown as our heat. So we can easily do the properties, right? So let's start there. So if we have our properties that are 400 Kelvin that was set above, we go to our table. I'm just going to write all these down. So we have CP, 1014 joules per kilogram Kelvin. We have dynamic viscosity, 230.1 times 10 to the negative 7 Newton seconds per meter squared. We have Prandtl number, it's 0.69. We have thermal conductivity, it's 0.0338 watts per meters Kelvin. All right, so a bunch of properties wrote it. All right, so we have CP. All right, so then we have our one equation of the COE, but two unknowns, right? So where else can we go from here?
Can we do the special case of the uniform surface heat flux and find what that actually is?
Okay, so we have, yeah, so we have this uniform surface heat flux, right? So let's just, we're not even go grab equation from that. We're going to figure this one out because it's simple enough that we can't based on other equations we've done. All right, so if we think of what we have for Q right here, right? But we have Q there, but the surface heat flux is constant. Can we go from that Q to heat flux?
Yes.
How do we do that?
With the area.
Yeah, so if we just did heat flux times our surface area, yep, so we would have pi dl is heat, right? So that means what we have above, heat flux from above would be this. So I just inserted this to solve for this, with this being COE, right? I mean, we can go through again. We have inlet, still don't have outlet. We have CP, mass flow rate, pi. We have diameter, we have length, okay? And we don't have heat flux, okay? But we know heat flux is a constant, okay? So let's go look at our schematic. Is there any way we can figure out our heat flux? Remembering it's constant over here, right? It's constant right here, it's constant right here, it's constant here, 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 and here. It's the same heat flux. Can we possibly use one of these additional kind of givens they have for us? So this one right here, okay? So we have this surface temperature at the outlet given, right? How could we utilize that with the heat flux? How can we relate those two temperatures right at the outlet, the surface and the mean?
Go ahead.
Either say they're the same, or it would be that they're an average or something near it. Like that's it, the surface outlet and the mean outlet.
They're not they definitely can be different, right? But what equation do we have that relates those two?
Newton's law of cooling.
Yep. Yeah, right at those points is what relates those 2 points to a heat flux. We have convection. That's what's going on at the outlet to that surface. So if we do Newton's law of cooling, yeah, we can do it with the surface, it's fine. Which one was? Surface. Okay. So if we do surface to mean outlet, now we have, so this is just the convection at that exit, all right? Now we have another equation for the heat flux. And if we look at this one, we still don't have the outlet, right? We do have the inlet. We don't have the convection coefficient or the heat flux, right? But if we utilize these two equations are now together and set them equal, the only unknowns we have are the outlet and the convection coefficient, right? So what do we need to do next then? So if we set these two equations equal to each other, we still have two unknowns. So we either need another equation that relates the outlet temperature, all right? Or we need to figure out our convection coefficient, right? So which one do you think we can do? Any ideas?
I would do the convection coefficient.
Yeah, so our convection coefficient, right? So we already said no, we haven't determined anything. All right, so we need to figure out our convection coefficient, right? Okay, so if we're going, I'm messing with All right, so convection coefficient. What do we need to determine to go in our book and get the right equation for the convection coefficient?
Reynolds number.
All right, okay, so we need to figure out Reynolds number, right? Okay, so we have mass flow rate. I already got the dynamic viscosity diameter. So we get 1494, which is our less than our 2300 for internal flow. So we're laminar. So we figured out whether we're laminar or turbulent. So we're laminar. We know that much. Anything else? To get our convection coefficient? What else? For internal flow. What else did we solve in the last problem?
The entry length.
Yeah, entry lengths. Okay, so for laminar, our equations look like this. Fully developed hydrodynamic. Oh, yeah. Okay. And if we solve these, we get 0.74 meters and 0.51 meters. Okay. And our length, it's 2 meters in this problem. So what can we say here?
Fully developed.
Yeah, so we're fully developed. Write this a little nicer. Fully developed. I'm going to run out of space. Hydrodynamically and thermally. Okay, so now we know we're laminar and we're fully developed, right? So there's also whether we want local or average convection coefficient. So if we're solving at the exit, which one are we looking for, right?
Local.
Yeah, we're gonna look at local, right? And we already know we're internal flow, right? So the geometry is internal flow. Okay, so we have these 3 things that help us define and go get our equation, right? We also have our boundary condition, which is our constant uniform heat flux, right? So that's what ends up with all these things. So So laminar, fully developed, local, constant heat flux or uniform heat flux. We get Nusselt number is just 4.36. So it's a single value for the Nusselt number. But we also know that Nusselt number is H times the characteristic length, which is diameter and internal flow, over the fluid's thermal conductivity, right? Already got this diameter we have. Now we have Nusselt number. So we can utilize that to get our convection coefficient. So our H value is 14.74 watts per meter squared Kelvin. If we work our way back, now we have enough to set these two equations equal for heat flux. We have the convection coefficient. We can solve for our outlet temperature. Which is 146.3 degrees Celsius. And then we can go way back up to the top and use our COE. And we get a heat of 12.7 watts. Any questions?
Where did you get the Nusselt number from?
The Nusselt number, so that's just the equation from inside the chapter.
It's on page 378.
378.
Never mind, I found it.
8.53.
3.
Yeah. Yeah. So 8.53. And then you see another constant value for surface temperatures, 8.55. Okay. But we're using the 8.53. Okay. All right. So we have then our heat. Was there any other questions? All right, so part B is the length is now 0.2 meters. What happens with the exit flow conditions and how is the convection coefficient affected? Is it going up, down, or staying the same? Okay, so we have now part B, the length is 0.2 meters. We got to figure out flow conditions. All right, so let's go back up here. All right, nothing with length yet, flow conditions. This is all temperature. So if we are here, we have a length of 0.2 meters. What changes?
It's not fully developed.
Right, so the Reynolds number is still the same because that's just mass flow rate and viscosity, or dynamic viscosity. So we are still laminar, but not fully developed. What do we think happens to to our convection coefficient. Does it go up, down, stay the same if we're not fully developed? All right, so if we're looking at, like with length X, if we're looking at how that convection coefficient changes, starts off high. Oops, this curve a little bit different, and then it becomes a constant value right here, and that's fully developed. And here's H. Okay, so what do we think our H, our convection coefficient is?
It'll be high.
Yeah, it's going to be higher, right? So while we're not fully developed, our H is higher, right? Greater. Okay. We could also go and solve it. Okay, so that would just be going and grabbing the value from figure 8.10A, because we're looking for the local, and that would, or equation, let me go grab the equation number here. .58. .10 works because we have a Prandtl number of 0.7. 8.58 works at all kinds of different Prandtl numbers. Okay, so those two places would work for this problem. We would just need to get this Gratz number. That's used in the figure and in the equation. And that just looks like Gratz number to the -1 is just, in this case, we're looking at length, at the whole length, L over D, Reynolds number, Prandtl number, okay? And that's what you can utilize to get your Nusselt number. You can also just look at those figure 810, and that shows you how the convection coefficient changes, because it's showing you how Nusselt number changes during the entrance region and then when it's fully developed. Part C is now the mass flow rate is 10 times the original mass flow rate. So they want to know flow conditions. So let's look at that. What happens if the mass flow rate is 10 times the original mass flow rate?
Becomes turbulent.
Yeah, so now we have, this is 15,000 Reynolds number. Okay, so we're turbulent now, okay? And then the next part is asking whether H, the convection coefficient, will be greater, less than, or the same. Do we have any ideas here? we have all that extra inertia and mixing and chaos within the flow, what do we think that does to the convection coefficient?
Is it lower?
What was that? Sorry.
Lower it?
No, it actually increases it. It moves that heat better, right? If you got, let's take a look at this, our schematic, right? If we have turbulent flow, it's gonna, it's chaotic and moving flow, so it's gonna move things better from this center point here to the wall, which is what convection's doing, that Newton's law of cooling with the motion, okay? So that is when you have that chaos of turbulent flow, it's doing that better, okay? Where laminar flow, it's, this nice streamline, so it's not moving that that energy from the middle to the edge as well, right? So our convection coefficient goes up, okay, and we can get that value from, well, we can check whether it's fully developed turbulent flow, and that would just be L over D, which is 2 meters divided by 0.01 meter, which is 200, which is because it's greater than 10, is fully developed. So fully developed turbulent flow. So then we can just use our relationship, the Ditus or Ditus Volter correlation. Okay, so depending upon these different conditions tells you how you have to get your convection coefficient, get your Nusselt number, which gets you your convection coefficient. Any questions? And that's it for today. You guys and gals have a good rest of your week. And we'll have class again on Monday. Okay.
Have a good week.
Yep, you too.
Thank you.